In this video, we're going to talk about cost. Okay, so we're going to start to look at applications of linear functions. So the first one being cost. So sort of intuitively, we know that cost is, it's like how much one person or one party pays for something. That's just sort of like a rough intuitive definition of what cost is. So let's start to explore this idea with an example. So in this example, I'm continuing my numbering from the previous videos in this section. So in the last video I did example 1, this is example 2. So this says that Lyft charges riders $1.80 on entering the car, plus $1.25 for each mile that's traveled. Let C of x be the cost of riding x miles. Okay, so in part A, I want to graph C as a function of x. Okay, so what I'm going to do is I'm going to start to draw an xy axis. So I'm going to start to draw some axes. Okay, and then this is going to be my x-axis. The other axis, instead of being y here, it's going to be c. Specifically, it's going to be c of x. That's going to represent the cost. Okay, so on the x-axis, let's just put some tick marks. So let's say I go 1 mile, and then 2 miles, and then 3 miles, and 4 miles. And I want to know the costs of traveling those distances. So let's make a table of values. So I'll have x, I'll have c of x. So let's just start with 0. Let's just say for some reason we decided to take a lift. We got in the car, but we didn't travel anywhere. We just got right out. So in that case, Lyft still charges us $1.80 for getting in the car. That's sort of like a flat fee that we always have to pay, no matter how far we travel. So $1.80. Now what about if x is 1? Well, if x is 1, we pay that $1.80 plus this $1.25 for traveling 1 full mile. So if I add $1.25 to this, I'm going to get $3.05. And now if we travel 2 miles, now I pay another $1.25 on top of this. So that's going to be $4.30. If I travel 3 miles, that's an extra $1.25. So that will be $5.55. And if I travel 4 miles, my cost would be $6.80 after adding another $1.25. Okay, so now on the y-axis, or I guess the c-axis here, let me put some tick marks. So I'm going to space these out every 2. So I'll go 2, 4, 6, 8, 10, just because in the vertical direction, I seem to be covering more ground. So that's why I'm spacing out these tick marks a little bit more. That's why my scale is different here. Okay, so now let's plot these points. So when x is 0, the y value is 180. So that's going to be somewhere here. That's my y-intercept. When x is 1, the y value is 305. So that's a little bit above, a little bit above the midpoint of 2 and 4. When x is 2, my y value is 4.30. That's maybe somewhere here. When x is 3, my y value is 555. Maybe it's a little bit below 6, so somewhere here-ish. When x is 4, my y value is 680, so maybe somewhere here. Nope. Okay, so we have these points. Okay, so if we were to connect these points, this looks like a line, or more technically, it looks like a linear function. Looks like a linear function. In fact, let's go ahead and connect those points. So if I do that, I get this hopefully straight line, assuming my drawing is reasonably okay. And it would continue past this if I traveled more than 4 miles. It would keep going. It would keep going forever this way. Or maybe it would stop when the gas ran out of. Maybe it would stop when the car ran out of gas or something. But let's just say it continues like this indefinitely. So because I have this linear function, let's try to write the equation of this line. So I have two choices in terms of my review from the last video, either slope-intercept form or point slope form. For this line, we know the y-intercept. So y equals mx plus b is easier. Okay. And that's, I would say in general, that's rare. It's rare where y equals mx plus b would be the easier one. Usually point slope form would be easier because typically we don't know the y-intercept. But here we do. So my y-intercept b is 1.80, or I could write just 1.8. And my slope is how much the y value increases. So it's how much the y value increases when x increases by 1. So when this is 1, what is this change in y? Let me write delta y. What's my change in y? Well, that's 1.25. Okay, so my slope here is 1.25. It's how much my function changes when the x value changes, well, I guess technically increases by 1. All right, so that's my slope. And because we're talking about a cost function, this slope has a meaning. This represents what is called the marginal cost. So the marginal cost. And the marginal cost, let's write that a little bit better. Let's box this better. So the marginal cost. The marginal cost is the cost of one more item. So if I wanted to get one more item, or in this case, travel one more mile, how much extra would that cost? In this case, it's $1.25 for every extra mile that we traveled. Okay, so that is our marginal cost. Let me highlight this. This is a key term for this section. Okay, so now let's actually write this as a function of x. Okay, so when it says to write c as a function of x, what that means is to write a formula for c of x. And the formula should be c of x equals something where the only variable on this right-hand side is an x. But now we could write the equation of our line. C of x equals, well, the slope is 1.25. That's m times x plus b, so plus 1.80. And that's c as a function of x. And in this equation, these different parts represent something. So this 1.25 times x, so multiplying this marginal cost by x, by the number of miles traveled, that is what's called the variable cost. And that's called the variable cost because it changes, or another word for changes is it varies, and that's why it's called the variable cost, because it varies. It varies based on x. In this case, based on how many miles the lift has traveled. The 1.80 is also a type of cost. This is what's called a fixed cost. It's a fixed cost because it's not changing. This does not change based on x. So a fixed cost is a cost that does not change. A variable cost is a cost that does change or does vary based on my variable here, based on, in this case, it was x. All right, so these are two other key terms, variable cost and fixed cost. All right, so let's do the next part of the question. What is the total cost of riding 16 miles? So I have this cost function. If I want the cost of riding 16 miles, let's just plug in 16 for the x. So c of 16 gives me 1.25 times 16 plus 1.80. And then working that out, that gives me 21.80. And cost has units, so this should be in dollars. So this is in dollars. And if I really want to be precise, when I wrote my cost function in the previous line, I should have specified those units. This was dollars, so I should have done that. All right, so let's answer another part of this question. Now, part D. What is the cost of the 16th mile alone? So I don't want the cost of traveling all of those 16 miles. I just want the cost of getting from mile 15, where that finished, to mile 16, to finishing mile 16. Okay, so I want to do this in two ways. And both of these ways are going to be pretty quick, but I want to talk about both of them. So method one. So if I want the cost of the 16th mile alone, so on its own, just mile 16. One way I could do this is I could take the cost of the first 16 miles together, so the total cost of the first 16 miles, and I know that's 2180, and subtract the cost of the first 15 miles. Because if I do that, that gives me the cost of the 16th mile on its own. So the first 16 miles, that cost is C of 16. First 15 miles, that would be C of 15. So I know C of 16 is 2180. C of 15 is going to be something. Let me just put like a squiggly line here. And if I were to simplify this, if I were to plug in 15 and then subtract these two, it turns out what I would get is I would get $1.25. And if that number looks familiar to you, that's good. And that's important. It should look familiar. This showed up earlier in the problem. And it's going to connect to the second way of doing this. So method two. So if I want the cost of just the 16th mile alone, I can remember that the problem told me how much each additional mile costs. So each additional mile costs how much? It costs $1.25. That's what the problem said at the beginning. Okay, so the answer to this is $1.25. So you might remember this as the marginal cost. That's what this question is asking. It's asking, well, what's the marginal cost of just the 16th mile? So because my function is a linear function, that marginal cost stays the same, no matter what mile we're talking about. So this method, method two, where I just took that marginal cost and I applied that to this specific mile marker, this method works, doing it this way, just for linear functions. Because for linear functions, that marginal cost is not going to change. But if my cost wasn't a linear function, then I could still do it in method one in this way. And this would work for all functions, not just linear ones.